Welcome back, students, to the continued lecture on flip-flops. Gurukul lectures are a wonderful opportunity to reach out to you and to understand that what are the things that technology today has taken us to. So we were discussing how to speed up the flip-flops. Flip-flops, as we found, require the clock, and the clock can be as previously discussed, they were all level triggered. Now level triggering is fine, but when the larger number of components are involved, then we have some speed issues. A case being that typically, like we discussed in our last slide, that we processed 4 bits. Now this is just an example. A movie that you see or streaming we see is in Mbps. So what happens is, how do you process this data at a high speed? And in order to make, even with those computer games, how do you have these graphics and this movement where you process tons of data? So in order to speed up these digital devices, the scientists, they modified the level triggering to edge triggering. Edge triggering has, in this case, a change of state from high to low or from low to high. So the basic circuit is always a capacitor and a resistance. So what we find that if we give a square wave input to a capacitor and we take the output across a resistance, then it gives out the output as spikes. These spikes are like edges. So if we had initially microseconds of level triggering, now we can go to nanoseconds of edge triggering, and hence we find that microseconds to nanoseconds is a jump of 3 orders of magnitude, that is 10 to the power 3. Nanosecond is 1000 times faster than microseconds. Why this need? This need is there because when we are processing GB type data, gigabytes of data, then we require these many flip-flops. So a microsecond will be huge when we have a million component, whereas a nanosecond will be much faster in its comparison. So we can understand here, again looking at the truth table of edge triggered D flip-flop, that till the time the clock is 0, there is no clock, then D input is again a don't care, and the next state output of the flip-flop is the last state. At the rising edge of the clock, when D is equal to 0, the output, that is the next state of the D flip-flop, is 0. Again, with the rising edge of the clock here, when D is 1, the next state of the D flip-flop is 1. When clock is the falling edge, then again, irrespective of the input being given to the D, that is again a don't care, we always have the output fixed as the last state. So what we infer from this truth table? Number 1, if clock is 0, then this D flip-flop is behaving as a memory element. If the clock is the falling edge, as in the last case, again the D flip-flop is behaving as a memory element. And when the clock is the rising edge, then we can input new data in the D flip-flop. So edge triggered D flip-flop is realized by making its RC time constant R and C. When we multiply the resistance and the capacitance, then we get the unit of time, as we already know from our basic physics classes. So the RC time constant is much smaller than the clock's pulse width, and because of this the capacitor can charge fully when the clock goes high. This exponential charging actually produces a narrow positive voltage spike across the resistance. Later, the trailing edge of the pulse results in a narrow negative spike. So the positive spike is the rising edge and the narrow negative spike is the falling edge. So the narrow positive spike enables the AND gates and the narrow negative spike does nothing. This kind of operation is called the edge triggering because the flip-flop responds only when the clock is in transition between its two voltage states. The triggering occurs on the positive going edge of the clock and hence it is referred to as positive edge triggering. So the timing diagram for a positive edge triggered D flip-flop is just like this. On the top, first is the clock, and in this figure we can see there are three rising edges. So for the first rising edge, when we have the inputs, we find that the D input is 0 and hence Qn plus 1 is shown to be 0. At the next rising edge, we find that the D is high and hence the Qn plus 1, which was 0 thus far, will change its state from 0 to 1. At the third positive or rising clock edge, we find that the value of D still remains 1 and we find therefore that the Q level goes to 0 because there is a midway transition. So we also include two special operations within the flip-flop. One is the preset and one is the clear. As the names describe, the preset means feeding in a particular value, in this case either the 0 or a 1 inside a flip-flop, then it is known as preset, and clear operations are those operations which are used to clear out the memory contents of the flip-flop. The AC or the all clear button on the calculator actually does the clear operation. So we know that when the power is first applied, the flip-flops, they come up with random states. Random states implies they can have a 0 or can be a 1, which is just randomly. They will either have a 0 or a 1, but it is actually a random distribution. And to get the computer started, we find an operator has to push the reset button. So this sends a clear or reset signal to all the flip-flops, and also in some digital systems it is a preset is necessary to feed in the data to the flip-flops. That is why when we boot up a computer is a digital device, a mobile phone is a digital device. So when we actually shut down the computer or a mobile phone or a tab or any digital device, it takes some time to start up when we push the start button. The computers, they check the BIOS, and what we see is that it gives a stable output only after a couple of seconds. Same thing happens with the digital TVs that are there nowadays. You can hear the sound coming in before the computer, which is your television nowadays, it actually starts. These Android TVs that you have, when you switch them on, they do not switch on instantaneously. They take up some time to boot up. And this is where the preset and the clear operations are being implemented from inside the motherboard, which has the master IC that controls all these operations. So what are preset and clear operations? As can be seen in this figure, that we have a preset that you can see is fed to our OR gate at the top. So this preset will allow a 0 or a 1 to be processed along with the output of the AND gate, which will finally act as the input of the SR flip-flop. Similarly, with the clear, one should not be confusing this clear and the clock signals. The clock signal is to drive the flip-flop, whereas clear is to clear out the contents or reset the contents of the flip-flop. So this figure shows the typical terminology that we are using in this case. We have positive edge triggered flip-flop. The negative edge triggered has a small O before the trigger signal, and we also have the level triggering. So before we move further, we need to understand that there is some switching time involved with the flip-flops. This is because the flip-flops are actually storing data where the voltage is being applied to the analog components, and these analog components are designed to function in only their saturation and cutoff regions. Mostly transistors, bipolar junction transistors are used, and they are configured in such a way that they do not show their output at their active region after we draw the load line. According to the load line, these transistors, BJTs, they function only as a switch, that is, they are either conducting maximum current, which is in the saturation region, or they are in cutoff, that is, they are not allowing current to pass. So these transistors, being physical devices having actual flow of electrons, cannot switch on and switch off instantaneously, and hence they take some time to change their state, and these are popularly known as flip-flop switching times. So there are three types of switching terminology associated with the flip-flops. Number one, the propagation delay. Propagation delay is defined as the amount of time it takes for the output of a gate or a flip-flop to change its state after input changes. For example, typically for a D flip-flop, it takes about 10 nanoseconds for the output Q to change state after D input has changed. Okay, so this also happens in a class. Sometimes when we are being taught, some of us understand the concepts very fast, whereas there are students, there are our colleagues, there are our classmates who understand the same concept after a delay of a few seconds. That is typically propagation delay. In this case, the mentor teaching the class is the input, and whatever he or she says has to be imbibed or understood by us. Sometimes we take more time than our peers in the class, and hence the propagation delay. Now, one thing to note here is that we can always see that okay, D flip-flop takes only 10 nanoseconds. For us, 10 nanoseconds is 10 to the power minus 8 seconds. 10 into 10 to the power minus 9 seconds is 10 to the power minus 8 seconds. For us, the time is already very small. But the thing to note here is that when we have millions of components and maybe going to billion, then this would 10 nanosecond difference with each flip-flop will become a significant amount of time for us. A very typical case that we see is that if we had been using the computer, maybe a laptop or any digital device for process our data, and we have to watch a movie, then we may have to clear out its cache memory or even switch off and again switch on the laptop all over again. That's because with continued usage, we have the memory filled with data that needs to be cleared out. Sometimes we see that the movie runs in a perfect fashion on our friend's laptop who has a higher amount of RAM compared to our own laptop, which has a lower amount of RAM. So we say it is a RAM problem. RAM problem means because RAM allows you to process data. Higher the RAM, more the data it can process at a given point of time, and hence with parallel processing we have less delay. But if the RAM is limited and we have only a set number of flip-flops, then the total delay time would add up and it would slow down the processing of data by our computer, and hence its output would get affected. So after propagation delay time, we have another set of definition of time that is known as the switching time. So that is the setup time. Setup time is defined as the minimum amount of time that the data bit should be present before the clock edge comes in. Typically, it is of the order of 5 nanoseconds, or for slower ones, it's 15 nanoseconds. So what is the setup time? Setup time means that the data at the input of the flip-flop should be stable or should be present before the clock edge comes and changes or helps transit the data from input to the output. In this case, from the D input to the Q output. That means data at the input should be stable before the clock edge hits. The third one is the hold time. Hold time is the minimum amount of time that the data bit D, in this case for the D flip-flop, the data bit D must be present after the clock edge arrives. That is, the clock edge comes and the data is processed, and the same data should be present before or for a certain amount of time after the clock edge comes and goes. That is, typically a setup time is of the order of 15 nanoseconds, the hold time is of the order of 5 nanoseconds, and propagation delay is of the order of 10 nanoseconds. So it means that the data should be stable for 15 nanoseconds initially, that is the setup time. Then we have 10 nanoseconds of propagation delay, and the hold time is of the order of 5 nanoseconds. So adding all of them up, we see for a stable data input to be processed from D input to the Q output, we have a total propagation delay of 15 plus 10 plus 5 nanoseconds. That is, it takes about 30 nanoseconds typically for a data bit to be processed from the input to the output. So in this case, we conclude that if a data bit is being processed in 30 nanoseconds, then to process high amount of data, we need lots and lots of flip-flops, and therefore we need to have a very fast clock as the input. So the problem that we still remains with the use of SR or RS flip-flop is that out of 4 states 00, 01, 10 and 11, we are unable to use almost 25%. That is, we do not allow, or we are forbidden to use the inputs S equal to 1 and R equal to 1. So another type of flip-flop is designed, which is known as the JK flip-flop, which is used to overcome the problem of S and R flip-flop. In this case, we will see that it allows, again, there are only 2 inputs, that is J input and K input, and hence there will be 4 combinations of 00, 01, 10 and 11. So we'll see here that both J equal to K equal to 1 input is allowed in this case. If you look at the figure that is shown over in the screen, we find that basically we have SR flip-flop with 3 input AND gates being connected to S and R. One input is common of both the AND gates, and which is the clock. For the upper AND gate, it has the J input, lower AND gate has the K input. And we find it is interesting to note that the upper AND gate has one input coming in from Q bar feedback, and the lower AND gate is having the Q output feedback at one of its inputs. So again, till the time clock is 0, irrespective of the value of J and K, that is XX, we have the output fixed at Qn. The output Qn plus 1 will be its last state, and hence this JK flip-flop will behave as a memory element. When the clock goes high, that is, we have in this case the rising edge, then J equal to K equal to 0 will again give you the output as its last state. When clock edge is high, J equal to 0, K equal to 1, then the next state will be 0. Clock edge high, J equal to 1, K equal to 0, the output is set at 1. And the surprising result in this case, when clock is high and J equal to 1 and K equal to 1, then the next state would be the complement of the last state. This is a very surprising result, and this surprising result will be very useful for us to design future circuits of counters, as we'll see in the next few slides. So the JK flip-flop, when J equal to 0 and K equal to 0, we'll see that both the AND gates are disabled and the clock pulse has no effect, and the Q value, the output value, retains its last value. That is, the circuit itself behaves like a memory element. When both J equal to K equal to 1, the output depends on the state of Q or Q bar. If Q is high, last state is high, then the flip-flop will be reset, and if Q equal to 0, the flip-flop gets set, that is, the next state is 1. Hence, looking again at the truth table, we'll see that for all clock edges, when J equal to 1 and K equal to 1, its output Qn plus 1 will keep toggling. That is, for every change in clock, it will keep toggling between 0 1 0 1 0 1 0 1 or 1 0 1 0 1 0 1 0. It will go on forever till the time the clock edge goes high every time. So what is toggling? The toggling refers to switching to the opposite state, and this switching of the output of the JK flip-flop when its inputs are both J equal to 1 and K equal to 1, this will keep on going on till the time we have the clock running. So there occurs a problem of racing with this toggling. If the toggling happens more than once during one clock cycle, then we have the problem of racing. That is, the user, that is us, we cannot infer for sure that the output of the JK flip-flop was 1 or 0 when J equal to K equal to 1. So we have to overcome this problem, and only after overcoming this problem can the JK flip-flop be used for all the 4 combinations. So what really happens is, there are 2 methods in order to overcome this problem of racing. One is the edge triggering, and next one is the use of master-slave technique. So we'll discuss the master-slave technique in detail. So what we do in order to overcome this problem, we either use edge triggering. With edge triggering, we can understand that edges are much faster than levels. Like I typically said, they are 1000 times faster typically, and hence there is no toggling in between, and hence we have a stable output. Whereas if we are using level triggering, then we have to break up the JK flip-flop. By breaking up, I mean that we have to use the master-slave configuration. That is, instead of using one JK flip-flop, we'll be using two JK flip-flops to process the data. However, both the JK flip-flops would not be used at the same time. So if you look carefully at the circuit, we find that the JK flip-flops do not have the same value of clock at a given point of time. For the first master JK flip-flop, if we have the clock at high, then the clock would be low for the slave, and vice versa. So if J is equal to 1 and K is equal to 0, the master sets the flip-flop on positive clock edge, and the high Q of master drives the J of the slave at the negative clock edge, copying the action of the master. So in this case, the basic idea is to use the propagation delay to our advantage. So what we see here is that the J input on the extreme left is the input in the master, and output is being taken from Q, that is the output of the slave. In between, there is a propagation delay, and master and slave do not switch at the same time. So we will discuss this one further, and we find that when J equal to 0 and K equal to 1, then the master is reset, Q is 0 at the positive clock edge, and at negative clock edge, slave is reset, giving Q equal to 0 finally. When J equal to K equal to 1, then in the master, then it toggles on positive clock edge and the slave toggles on the negative clock edge. Regardless of what the master does, the slave copies it. If the master sets, slave also sets, but not on the same clock pulse. We'll discuss this further in more detail in our next lecture, how master slaves prevents racing in JK flip-flop when both J and K have same value of input, that is 1. Thank you so much.